And we're live. Let's see where we ended up last time. Did I do anything? No. Okay, so the code is clean. Gonna run a test. Yeah, our proof transfer from was failing. I'm not gonna fix it this time. In fact, I am just going to delete both of these. And we'll try to fix them at a later date because there is something really cool that I want to try today. We have 12 tests, they all pass. So I found this while looking at the read the docs for Solidity. And this is a complete ERC20 example in YUL, which is very interesting because it has a few of the things that I talked about. So let's try them out. I'm gonna just copy the code onto, a token.yul file. And let's see, there's no YUL, but does this work? Yeah, so the compiler is expecting actual Solidity, so don't mind all of these errors, but this should look okay. And let's see, what does a YUL file looks like. So we have an object token, code, and runtime. So if we compile this and we create a new contract of this, code is, it would be, like the constructor, and then runtime is what ends up being, the actual code that's on the blockchain. So what does this do? This is actually pretty easy to follow, so maybe we'll do a rundown. Store the creator in slot 0. So this is an S store on the 0 slot, the first one, of the caller. This is really, what everybody does. Owner equals message.sender in the first slot. So pretty easy. And then it deploys the contract. It data copies starting from 0, data offset runtime. So it starts here, data size, the size of runtime, which should be everything. And then it returns, this is the return of the call, which, if I remember correctly, it's like everything's okay, and the size of the bytes that were copied, I guess. Let's go over this. The code. Protection against sending ether. So way back in Solidity, you could, I don't know if this was in version 0.3 or 0.4 something, when they added payable. This is what prevents, sending ether to any contract that doesn't have a payable function. So what it does is it requires that the call value is 0, otherwise it reverts, right? This is the first thing that it does. Well, when we actually compile this, there's going to be a couple of opcodes first for, initializing memory or, one of those. But we just want to go over this. So there are no functions here that take in ether. So normal ERC20 token doesn't really require any ether. So this is what's going on here. And then this is the function dispatcher, which I discussed a couple of episodes back. Switch on selector. So selector is most likely a function here. It is a function that takes an S, no, that returns an S. And what does it do? It just grabs call data load 0. This is probably, the first 32 bytes. And it divides by this. So what? It's gonna get the first 8 bytes. And this is usually what, if I do set call data, whatever, balance of address, and you give it an address, it's this first 8 bytes. So whatever you send, we just want to get the first 4 bytes. And we know what, and here you can see 70A0A231. It's this, so it's the signature of balance of, and so on and so forth. So here, if we wanted, we could really, because, if you call mint, and let's say mint is your most used function, every time somebody interacts with your contract, it's going to say, did you call balance of? No. Did you call total supply? Did you call transfer? Did you call transfer from? Did you call approve? Did you call allowance? Did you call mint? So it's 1, 2, 3, 4, 5, 6, checks, which all cost gas until you get to the one that you actually wanted. So one thing we could do is say, what do we want? What do we think is going to be the most used, right? And put those up. And the default is just to revert, right? If we're not calling any of these, we revert. What else happens? So if it's balance of, these are all functions, right? So return uint, balance of, decode as address. Let's look at decode as address. It decodes as uint. So decode as uint gets an offset. So this is all extremely low level, right? But it figures out which position to read from call data. Okay. Less than, call data size less than, this probably for, just a sanity check for this. And then it loads from a certain position in call data. And decode as address, what it does, it most likely checks that we only need 20 bytes for addresses. And then what? Balance of. Let's look at that one. Balance of. Yeah, account to storage offset. This is just for mappings. They're saved as a specific way. And then it S loads from whatever slot, returns the balance. Let's see a couple of others. Owner position. We know that it's 0. It S loads from 0. Total supply. It also does a simple S load from, it checks the total supply position. Mint tokens, does an S store. Safe add. So here we have a safe add. Utility functions. Less than or equal, greater than or equal, safe add. So it adds and then it checks that it didn't overflow. Called by owner. This is, what is it? Only owner in Zeppelin. So it checks that the owner and the caller are equal. Reverts if 0 address, requires an address. This is pretty well written. Oh, the events. I mean, it is low level, right? But we can work with this. What do we want to do? We want to compile this, get the bytecode, and use it here. So when we create our token, we want to, instead of running this token, we want to run this one. So let's see if we can make our token, because I prefer, if we're doing this live, I prefer modifying the solidity, and then the yield's gonna be easier for me. Let's see if we have anything here that is different from our token. Transfer from, mint. Let's look at mint, can only be called by the owner. That is fine. Mint tokens, add to balance, transfer, execute transfer. Approve. So approve cannot be called by the 0 address. Sorry, you cannot approve the 0 address. And execute transfer, you cannot transfer to the 0 address, which I'm pretty sure our token does not have. So we can approve, right? We can approve the 0 address. And so we're gonna change that. And anything else? Decrease allowance. Any other difference? Called by owner. Mint tokens. Does mint return something? Transfer, execute transfer. Does execute transfer return? Is this okay? Oh, yeah. Mint returns true. So does approve, transfer from, and transfer allowance. Yeah. Okay. So let's try to make our token a little bit more like the other one. So we said that approve, the spender cannot be 0. So let's say require how's that? Spender cannot be the 0 address. And same thing with transfer. And with transfer from. Although yeah, let's do it, although there are other ways to do it. Let's do it like this first. And what about, we said mint. Did we say that we could mint to the 0 address? I think we can. Add to balance. So it looks like we can mint to the 0 address, so let's leave it at that. We're gonna have to fix a couple of our tests now, maybe. Proof transfer is failing. This is good. And it gives us a counterexample. So what is this? Proof transfer. It says 0, address 0, 0. So supply 0, address 0, amount 0, right? We cannot. If the user is 0, it fails because we cannot transfer to the user 0. This is absolutely perfect. So we're gonna add another, let's say if the user is equal to the address 0, we return no transfer to address 0. Whoop. 0. Good, good, good. And now it's time to compile this, which I don't remember how to do. It's strict assembly, YUL mode. Switch to YUL mode, ignoring all options except machine, YUL dialect, optimize, and YUL optimizations, and assumes the input is YUL. Switch to strict assembly mode, ignoring all options except blah blah. Optimize, YUL optimizations. Think strict assembly and YUL optimizations. It's what we want. Let's see. Sol-C strict assembly source token.yul. If you wish to use the standard input, please specify the Sol-C options input file. Please specify explicitly this. Okay, this did something. Sol-C strict assembly token.yul. Can I optimize here? And did it do anything different? It did. So let's check. What is this? Token bin. Oh, this actually did something. But is it the thing we want? I'm gonna erase it again and strict assembly optimize. I'm gonna this into, I wanna put it in source token dot out. You're still experimental. Please use the output with care. We will. Token dot out. What do we have? The pre-printed source, which is the one that we already have. This is all good. Binary representation. This is the one we want. And then text representation. This is all the actual bytecode. This is what we want. This is the init code. And we're going to be using it up here. So what we want to do, and this I did try yesterday. So we have 0, like CXX, I need to change the token. Let's see if this works. CXX equals create. Well, let's start. Bytes memory code equals all of this. This is our creation code. And if I remember correctly, I'm gonna check this, but what was it? We need to add to the code, we need to add 32. let's double check that. And we unload the code. Pretty sure that this is correct, but I'm gonna double check it. Yeah. So that looks correct. Was it does only local variables to access storage? Okay. So let's do address of, I don't know. Can I have a variable named Yule? Say Yule is equal to that, and then maybe we can we do that? So instead of creating our token, we deploy a version of the Yule token here, and we create it here. That looks good enough to me. So let's test it out. Wow. And everything failed. Why? Oh, okay. One thing I forgot is that on our token, we have a total supply. And the Yule token starts with no supply. Also, this is not strictly necessary, but let's see, store, store. The owner is on the 0 slot, which should be up here because these are all constant. And the Yule token doesn't have any name symbol or decimals. We don't care about that right now. It has the owner in slot 0. Then, what else? Store. I have no idea, but total supply position, where is this? Oh, it is slot 1. Total supply balance of allowance. Pretty sure that is correct, but like I said, it's not important. Total supply, we're gonna remove this. So when it starts, there's not gonna be any total supply. So we're not gonna care about this. And in that case, we're gonna fix this one first. Let's do this. If true, we're gonna do that, else. We're gonna do this. So if we set this to true, we're gonna use our token. We set it to false, we're gonna use the Yule token. And let's see, what do we have to fix? Whole bunch of things. Test total supply, that fails. You know, transfer gas usage, whole bunch of things. Because we expected a total supply of this. So I think the easiest is gonna be just to mint to the owner. We're gonna mint that much. On the setup, right? easy. Now for the moment of truth. We're gonna use the Yule token. Okay, few things failed. Test burn bailed. Is that because we don't have any burn? Looks like it. Prove supply failed. Prove transfer and prove balance. Okay. So prove balance. Counterexample. The 0 address and 0. Prove balance. So what happens here? Oh, okay, that's right. So prove balance. If the user is 0 address and the amount is 0, we burn, so we start with 0 supply, we mint. That's right, we cannot. Didn't we say that we cannot mint? Well, here we can mint to the 0 address, but was it here that we couldn't? Save add, mint tokens. Function mint. Decode as address. Does the decode as address fail with the 0 address? Let's try it. Prove balance. No, so this wasn't it. Because the 01 address also fails the prove balance. Oh, okay, so what is the problem? With the amount also being 0. Prove balance. Oh, call burn. Oh, call burn. That is the problem, that there is no burn, not the other thing. Okay. We're gonna remove the burn. We're gonna start with 0 everywhere. We're gonna remove the test burn. We may add it later. I don't want this one anymore. We're not gonna mint any here. And the total supply, wanna oh, okay. This one worked. Prove transfer, prove balance, gas usage. Why did this revert? Probably because now we don't have any. And we have to mint whenever we start. That's okay. Rather we have these two as close as possible. We're gonna mint before each one of these. This is okay because it's a test mint. Gas usage, we don't want those gas usages anymore. Although, I'll test it as well. Okay, that looks good with the Yule token. Let's try with our token. See if we messed anything up. That looks promising. And I want to try something that let's see. This from Leonardo Alt. He is on the formal verification team at Ethereum, also working on Solidity. He said, equivalence check the compile sol versus compile Yule. And yes, verifying equivalence of the whole contract might be too hard sometimes. For those cases, you can also specify a function you want to verify equivalence in both contracts while ignoring all the others. Let's try this. HEVM equivalence. Now, how do we want to do this? Let's do this. So we have the two different tokens, right? We have this one, CXX. We can create CXX to our testnet, and we can, get the runtime code, which is this. And we can do the same for the other one. This is the code that will create, so Seth. So it is really doing this, right? Seth, send, create, and the creation code. It is indeed a lot smaller. So HEVM equivalence. You know what? Let's make a new equivalence.sh. And let's do sol equal Yule equal. This is the Yule code. And this is the Solidity code, which is, so this divided by 2, so around 2600 bytes versus, less than 1000 bytes. Let's see if they're equivalent. HEVM equivalence. Code A is sol. Code B is yul. Right? So, Vitalik, take the wheel, please, and see what happens. Not equal. Counterexample. Call data. Caller. Call value 0. 95D8. We've seen this one before. Let's go up. Oh, that's right, because do we need to delete this? Are any one of those? Is this something? Set call data. What is it? Name? No. Symbol? Look at this. 95D8 9B 41. This is the symbol. And this is 100% correct. The two contracts are not equivalent because there are 3 extra functions, at least, that we have on our ERC20 token versus the yield token. So I suppose the easiest would be just to do that. We're gonna do this again. And there are easier ways to get the runtime code than to do this, but you know, this is fast, so we're gonna keep doing it. Equivalence. So we've removed all of this, and we're gonna try equivalence again. And I can hear my computer. Okay, another counterexample. Call data 8D-A5. Is it one of these? $8D-A5? No. So this means that we have approved transfer, transfer from, mint. We didn't remove burn. And I will bet you anything that this is burn address uint 256 with something and something. So let's say 0x00. No. 9D-C9. Okay, so what is it then? If it is not burn, which, oh, we just have the amount. We don't have the address. So we're fine. It's gonna be this. God damn it. It wasn't. Burn uint 256. Do we have, oh, it's the owner? Because we don't have it public. $8D-A5CB. That's right. It's the owner. Okay, final couple of things, 'cause I want to do this before it's too late. Going to remove burn. This is not going to be public, so it is not callable. And am I missing anything else? Balance off. Balance off. Total supply, we have it. Transfer, transfer from, approve, allowance, mint. And we'll revert otherwise. And mint, oh, it's an address and a uint. It is good. Okay. Third try. Did we mess up anything on our tests? Let's see. We shouldn't have. We didn't. We're gonna keep this as true, and we're gonna create another token. We're gonna grab the address and we're gonna grab the runtime code. Put it into equivalence. And let's do round 4. I can hear my computer. The fans are going. I like that it's taking longer. Means it hasn't found any errors yet, or solver said unknown. That's okay. So Leonardo told us that this could happen. Verifying equivalence of the whole contract might be too hard. For those cases, you can also specify a function you want to verify equivalence while ignoring all the others. So how about we do that? So let's see equivalence. Code A text, code B text, signature test text. Sig. Let's try it. Let's try it with, let's mint. Let's mint not to the 0 address, but to the 01 address. Let's mint 1. That is our signature. Mint address UN256. Mint address UN256. Actually, let's copy this. And let's test it. Expected identifier but got number. Oh, just a signature? One, two, three, four, five, six, 7, 8. This should work. Seth, sig, with this. What? Expected identifier but got number. So is it really this? The actual signature? It is. Not equal for minting. Counterexample, call data. Mint caller. So it could be, and I hope this is the case, that, you know, there are different tokens owned by different owners. That could be the case. Let's try a different one. Approve. Not equal, again. So in this case, call data, approve, this is, but why in this case, why is this not equivalent? If I do balance off, like the simplest one there is, or total supply, will this get me something? Again, not equal. Call data, balance off, caller 0. Come on. Let's do the simplest freaking one we have, total supply. Okay, we got somewhere. Explored 2 execution paths of A and 2 paths of B. No discrepancies found. So we can say that total supply has no discrepancies. That is amazing. But why does balance off? Why are there discrepancies here? Counterexample. Let's see. Set call data, balance off address, which should be this. So balance off the maximum address. What should it give? Oh, we have them both deployed, right? So we should be able to check them. Do you want to do it? Yeah, let's do it the old way. Let's create this one again. So this is going to be, so Seth call the Yule version, balance off that has 0. Perfect. And now let's create this one and call the same. Set call balance off address. So, I mean, they both return 0, so no, not test, equivalence. If the caller is the 0 address, call value 0, it differs. So what are we saying? We cannot. So call value, this is fine because here we also have call value 0 and balance of Dakota's address. Well, I don't know. And I'm probably gonna leave it at that, but I guess we made some progress with not with balance of, but at least let's try that one again. With total supply, I want to see that one. No discrepancies found on total supply. That is good. Yeah, I'm gonna leave it at that. Token out, token Yule. Yeah, I'm gonna add everything to it. This is what, day 5. I'm gonna push it. Okay. So cool. If you want to follow along, you know, I'm gonna keep doing this at least 30 minutes every day if I can. And thank you. Hope you liked it.